semaphore. We'll do awkward silence. That's just the way it starts. All right, so what am I doing here? I had it in here for now. And we were doing it with, that's my choo-choo thing. Remember this one? Check it. Oh, that was so good. Here's our shared memory examples. All right, so we looked at two different shared memory examples, one using memory map, and then the other one using the built-in interprocess communication tool, shared memory get, which very well might be implemented in terms of memory map. All right, so these guys allow a piece of memory to exist outside of the PCB on our modern operating systems. Because really, this problem becomes bigger and bigger and bigger as we get to newer operating systems, because newer operating systems always have these levels of protection to protect one app from another app. For instance, the Android operating system, every single app runs in its own virtual machine. So if something goes bad with an app, the chances of that having an impact on the rest of the system are really, really, really small. I mean, I want to say basically nothing, but I suppose there could be a memory leak or something in the virtual machine that could cause an issue. But these guys are living in their own ecosystem, right? But that then creates a problem, because if this app is running in one ecosystem and this app is running in another ecosystem, how do those talk to each other? The only connecting point is the operating system itself, and the operating system would then have to provide facilities for that communication. And when we talk about interprocess communication, we're really talking about those potential facilities. So in a POSIX-based operating system, if we're talking about the official version of shared memory, we would be looking at IPC.h, interprocess communication.h, and the shared memory get and shared memory attach. So just to review this real quick, we had a couple of messages here. We went ahead and generated some shared memory. All right, so this is kind of very likely doing some sort of mmap under the hood, but whatever it's doing, this is getting some memory that's managed by the OS at that level. Okay, then we are giving ourselves a local pointer here by attaching to that shared memory. So this is giving us a local pointer that bypasses the local PCB and moves to the operating system level for this memory. Make sense? Okay, so that's what makes it global across our multiple processes. All right. Then we're copying the parent message into that shared memory. So this is just loading a string into that guy. This is a char pointer, so that's just a string in memory. So we just loaded stuff up there. We could have also written that with a for loop and copied some stuff up there, because we would just be storing chars. Not a big deal. Then we do the split here. If we are the child's going to read from that pointer, printing out the string it found there. So it'll find the parent's message, presumably. Then the child will overwrite that message with their child message, which was, goodbye. And then the child will prove that it's now been changed, and it'll show goodbye. The parent will immediately read the message, so they should see a hello right away. You do have a bit of something called a race condition here. Let's get that into our notes, because that is something that's going to be coming up pretty quick when we start talking about semaphores. All right, so how many of you have heard about race conditions? All right, what's a race condition?
Where the outcome of the code could be affected by how fast or what happens first.
Okay, yeah, so once upon a time, Dr. Martin Luther King Jr. So race condition is when you have, race condition is when you have two things or more. It actually is more common when you have more, but in our little example, we're going to say two things that effectively try to grab the same resource at the exact same time. The real life version of a photo finish in like race car driving or something like that, where two things may actually be able to grab the identical resource at the identical time. How is that possible in computing? Let's assume that we're both trying to access, I have to update. It just seems rude. Okay, let's. Because that would have, huh?
Why don't you just close out of that and keep going?
No, I would have had to close Keynote. It would have closed the application.
Are you sure closing out of?
That it said close the application.
Well, it said close presentation.
Oh, I understand what you're saying. You're saying why didn't I? Yeah, it said close presentation. Here, I'm just going to update just that one while we talk about this race condition, and everything should be good. All right, so we have two things. Let's just pick a resource. So let's pick a file, for example. We're trying to read from a file. And the reason I'm picking the file is because we think of files as being slower. So the chances of a race condition kind of become greater because read and write access to a file is a slower thing. So with that in mind, if I have two different processes running on the system, especially this becomes a bigger problem when you have a multi-core setup, right? If you have a single core processor that can only run one thing at once, it's borderline impossible to have a race condition. It's not actually impossible. In fact, I'm going to come back to that in a second. I'm going to ask you to give me a scenario how that could happen after I explain race conditions a little bit more example. But race conditions are definitely possible / probable when you have multiple things that can happen at the same time. So let's say we have two different processes, one running on CPU 1, one running on CPU 2. They both try to grab the same file at the same time. Okay? Now the idea is that when you open a file, you are opening it into your own memory space. All right? So if one of those guys had changed the file and written it back, this guy still has the old version of the file. All right? So you'd really want to protect the contents of that file from being changed by more than one person at once. So that way, when one person's changing it, somebody else can't read it until the change is complete. Otherwise, they're going to be getting an old version of it and possibly operating off of old data. Okay? So when both of these guys come in to grab that file, if we don't protect this file somehow, all right, because by default, opening a file for reading is not something you protect. Both of those guys are going to be able to grab that file and bring the current version of that file into memory. All right, then let's say this guy changes that file, writes it back out, and this guy goes and grabs it right before that write. Okay, right before that write hits disk, this third process comes in, reads the file, the unmodified file, right before the file becomes officially modified. So now this guy actually has out-of-date information. Does that make sense? Okay, so a race condition kind of works like that when more than one thing accesses the same resource at the same time. Sometimes this isn't important. So give me an example when we wouldn't have to protect a file from multiple processes accessing it at the same time. Go ahead.
When it's a template?
Tell me what you mean by that.
So like it's just like a default template for something, and one person's using it to use it for themselves, and then another person's grabbing it to use it for themselves.
Okay, so when you're not changing it.
Right.
Yeah, so if all these processes have no intention of changing that resource, let 50 people open it for reading. It doesn't matter, right? Now you're just burdening the file system. If it's a mechanical disk, it's going to be slower. If it's a solid state, it'll be a little faster, but it doesn't matter. Because at that point, if all those guys are opening that file for read-only purposes, just to get the contents of it, nobody's changing it, we don't have to protect it, right? But if one of those guys is going to make a change to that file, you do have the possibility of somebody, like I just described, trying to read the file one CPU cycle before the other guy wrote the file. And now he has out-of-date information, something like that, okay? So we can see that this is a real possibility in a multi-core system, when legitimately more than one thing can happen at once. Or in our common multi-core systems today, you might have, many of you have machines that have at least a quad core, right? And even on quad cores today with hyper-threading, you might have 8 logical cores. So that means that, without getting too deep into is hyper-threading really a secondary thing that can happen at once, you could do 8 things at once. We'll just call it that for right now. That's really going to up the ante on how many things could possibly have a race condition. That makes sense? Go ahead.
Do cloud storage like Dropbox have this feature? So if they detect it's open on one computer, another computer logged into the same account can't access it?
Absolutely. Sort of. And you've actually probably seen this before. If you've ever used cloud storage stuff, sometimes you'll get like a weird error message that says that a lock file couldn't be grabbed. You've seen that before? Something along the lines is usually called a lock file. That lock file is a form of protection. It's kind of a old school, it's a file system specific version of a semaphore. We're going to be talking about semaphores. We'll probably talk about the high level today and then use them in reality when we come back from break. But in any case, it's a means of saying that if 2 resources are trying to do something related to a file, they have to first check this lock file. And if the file is locked, they're not allowed to grab the resource. They have to go and they wait some random amount of time, then they go back and check the lock again. So it's that type of thing. Might be inefficient in some cases. So let's say that 5 of us are all trying to, a funny but good example of this is you have one outhouse at a sporting event, okay? One user at a time type situation, okay? And the door is going to be locked when somebody's in there. So it's considered to be fairly rude if you go up and just start like pulling on the door over and over and over again, whatever. But maybe you check it once and then you walk off and come back 2 minutes later, something like that. See if they're, done, whatever. Well, you might have 5 or 6 people who are all doing the same thing. So they might not necessarily gain access to the resource in a first come, first serve order, depending on how long it took them to return. But the hope is that through, possible trial and error, everybody eventually gains access to that resource because they finally go and check the door when it's unlocked. And then they're able to gain that resource, and then they immediately lock it. So they're locking the lock file. Make sense? All right, so now how might a race condition happen in a single core with a single core processor? Not that those really exist anymore, but let's assume they did. They do exist on small systems. Not really our general purpose computers, but smaller general domain-specific computing, they exist. But how could a race condition exist on that where multiple PCBs can exist, but only one thing is actually happening at a time on the CPU? And they're sharing CPU time, like we've kind of discussed. How could that happen? It doesn't say it's done uploading, or done downloading, but is it? That's not going to make a difference because those threads are sharing the same CPU time as the parent process. And if you're talking about processes within a process, the results of a fork, then those guys are getting their own process time. But this really comes down to the crux of a race condition, which is why I'm kind of throwing this example out here. It would be very unlikely. In fact, race conditions are often hard to reproduce, hard to kind of show an example of, because there's so many protections put into, and you can imagine that an operating system is going to have built-in protections to attempt to avoid race conditions, right? So it's often difficult, especially in multi-core systems, to mimic one of these guys, which seems backwards because multi-core systems, you think they'd be more prevalent, but multi-core systems also have a whole bunch of security put in that creates protections between the multiple CPUs. But how could a race condition exist on a single core CPU between two different processes trying to access the same resource, even though, well, here let's go back. Let's leave a computer for a second and go back to our outhouse example. So there's two processes, two people that want to access this resource, right? How can you technically, now a race condition would occur when both of them are granted access to it at the same time. Make sense? That's how it can occur. Okay, it's going to be a little awkward for a moment. Okay, and then usually the people will work things out themselves, right? Decide, okay, you go ahead and go first, and somebody backs out, so they recover from the race condition. And that's same thing with operating systems, right? We're not getting too graphic here, but the idea is that we would rely on people to probably figure out the problem if it did occur, right? Okay, so but a race condition first occurs, and then we could recover from that race condition using some sort of equitable stuff. But generally speaking, we have two people that are trying to access the that outhouse at the same time, but we're operating off of a single core. Now we're kind of mixing it together with computing here. How could they possibly gain access to that resource at the same time? When do they know that they are not allowed to use the resource? When the door is locked, right? Yeah. So you think about the process of open, you tell, well, I mean, nowadays they have like little symbols things. You really should just be able to glance at it and know whether or not you're being a jerk by messing with the door. But roll back a little bit before they decided we could have a little thing that just changed colors, which doesn't seem to be high tech, but they're very new, actually. This is kind of interesting thing. But in any case, there's a multi-step process to gaining access to that resource and then locking it down, right? You pull the handle on the door, notice it's unlocked, pull the door open, step inside, pull the door closed, lock it. So let's just call that 4 steps, okay? Okay, 4 steps. All right, we would call that not atomic. All right, so we're going to be discussing here in a second the idea of atomic operations. Gosh, are you serious? Oh, can I just say not now? Woot. I said I want a new one. All right. Out loud, we're talking about atomic, and it'll make it on the slides eventually. We're talking about atomic operations. These are operations that only take 1 step, where you're able to check, open, close, lock, all in 1 step. Okay? But in real life, that's 4 steps, correct? Ish. We just kind of created those 4 steps. So if we're thinking about this in a single core CPU type of scenario, okay, if I go and grab the handle and I check if it's locked, I have it now unlocked. So I've decided I can access this resource. All right. Then let's say that was the last instruction for my allotted CPU time. So where I'm going to pick up next time is I'm going to gain access to that resource. I've already unlocked it. We could even say I've opened the door. We can get through step 1 and 2 if we want. All right. So then we have a context switch. I'm going to leave the CPU because I'm out of CPU time. So I haven't finished gaining access to the resource, but I've already passed my internal check to see if I'm allowed to access the resource. Make sense? All right. So as far as I'm concerned, that resource is mine. But now I'm put on hold. I'm context switched off of the CPU. I'm getting in the back of the line, waiting for my next CPU time for this single core CPU. Another resource comes in, finds that it's still unlocked because I never was able to lock it. I didn't get that far because I was kicked off the CPU. They find out that it's unlocked. They go in, they lock it, whatever. They do all their stuff so that nobody else can check to gain access to it. Then let's say they run out of CPU time. So they're currently using the resource. They run out of CPU time. Finally, it's my turn again. I'm not going to run the code that's going to check to see if the door is unlocked or open the door. My presumption is the door is open. Okay, so I'm going to walk in and lock the door. So I'm going to lock a locked door. Now, I realize this starts breaking down when we talk about reality, right? Okay, because now you're just passing through a wall, the unbreakable plastic outhouse wall. Okay, but in computing, this can happen. Okay, so now we've grabbed this resource that's already being used. Now, in computing, we don't necessarily know it's being used because they have their own, copy of this thing in memory or something, where in real life, if you open it up, you're going to see a person in there. So now you back out and whatever. But in computing, you're not necessarily wise to the fact that it's being used, that somebody already has it. Because your feeling was that when you checked, whether it was locked or not, that was your check to see if it was being used. It's not your fault that the CPU kicked you out before you had a time to fully grab the resource. Does that make sense? Is this slow-mo? Slow. Children. It's Dr. Wall. All right. So we get the problem here. So in a single core CPU, you could have a race condition that could exist related to, just the random chance that somebody doesn't get to complete that action in the middle of their CPU time. So what are fixes for that? Because now we're talking about operating system stuff. So I mentioned a few minutes ago that we have, operating systems have a whole bunch of kind of, logic put into them to try to avoid race conditions. So what's the fix for that little scenario? So we just created a scenario where in a single core processor, two things could actually access the CPU or access the resource at the same time, even with what this generic idea of a lock file. How do we fix that? Well, first of all, let's identify what's the actual problem. Why were two things? We had to just in a single sentence say what was the actual problem. Why were two different processes, two different people able to access that resource at the same time, even though we put a lock on the resource? What was the problem? Why was it able to happen? Okay, that's true, but the uncontrollable timing only could occur because of the actual problem. What was the actual problem? Yeah, it's not atomic, right? There is a process between there's time that exists between checking the lock and grabbing the resource and locking the lock. Okay, there's a process there. And that's a period of time. And when there's a period of time, other things can happen during that period of time. In a single core CPU, that happens because bad luck, got thrown off the CPU. In a multi-core system, might not even be bad luck. So what's the fix? Make it atomic. All right, so now we're back to like a design pattern, right? So in real life, how does one gain access and lock an outhouse in one fell swoop? Okay, we're thinking about how do you take something that took 4 steps and bring it down into a single step, or at the very least, something that acts like it was a single step from the CPU's perspective. Say this again. Okay. Tell me more about that. That's you're actually going to 2 inter-process communication things later, but that's good. Tell me about that.
So when they call for the resource, they put it in a queue, and then it comes first process, checks it. If it's locked, they get back in the queue and wait until it's unlocked. And they keep checking it until it's unlocked, and the other processes line up behind them waiting.
Mm-hmm. So generate the McDonald's model. Right? You want to have access to the cash register, you get in line. Now, you've created a new issue though. First come, first serve on the line. Because now what if two people try to get in line at the same time? Then a Big Mac-induced fistfight occurs. Now, what we've done there is we have added a level of protection, but we haven't actually fixed the problem. Maybe we've even just moved the problem, right? So he wants to have a queue that feeds into the resource, but now the queues become our new resource. So getting into the queue in the right order, but it will if we deem that people getting into the queue out of order is far less important than people gaining access to, you're going to see it's called the critical area in our code. The thing that we don't want more than one person to change at once or be able to execute at once is called the critical area. We deem that two people ordering at the register is a far bigger problem than two people, butting heads a little bit over who was in line first. All right? Fair enough. So we certainly could do something like that and at least reduce the problem. Ultimately, this comes down to how do CPUs actually work. So we call, at the generic level, I've kind of advertised CPUs as being these things that perform various magic tricks, right? Where each magic trick is equal to one instruction on the CPU. But just because there's one instruction on the CPU doesn't mean that that instruction is atomic. That doesn't mean that that instruction happens in exactly one, what's called CPU cycle. Okay, so if we say that a CPU cycle is the minimum amount of work that a CPU can do, say that. If there is when you really think about things that happen on CPUs, they're really little computer programs that are built out of hardware. They're called data paths, but it's a hardware thing. Right, so it's a little tiny program that's a bunch of little gates and crap like that are hooked to each other that ultimately have a result. Now, if you only have a single AND gate, let's say, that's atomic, okay? But that doesn't solve a very complex problem. Now, one of the things we've mentioned about CPUs is that our low-level languages, we need to have our instructions be granular enough that they're generic and can be applied to lots of different problems. But that doesn't mean that they're so simple that they all happen in one CPU cycle. Several of them are doing, by CPU or low-level language standards, lots of things. They might take 15, 20, 30 CPU cycles to accomplish the result of one data path. Well, that means there's 30 opportunities for something else to occur on that CPU or in the operating system in the middle of an instruction, where a single instruction is interrupted. So how do we fix that? Okay. Well, so we're talking about scheduling. We have a couple. We mentioned earlier that we have this. One of the bad situations could be we created a 4-cycle example, right? Where it took after 2 cycles, the dude was kicked off the CPU. Right? Well, one thing we might do is say, don't let that happen. So we might do this. We might say, well, if the amount of time you're given on a CPU is in terms of cycles, and you're mid instruction, you got 2 options. You can either let them finish that instruction before you kick them off, give them a little bit of extra time, or you can roll back the instruction to the beginning of that cycle. What do I mean by roll back? What changes in a PCB in order for us to roll back to the beginning of the previous instruction? We looked at the PCB data structure. What's one of the things that the PCB data structure keeps track of? Yeah, program counter. What instruction should we execute next? Right? So if we are in the middle of an instruction and we need to bail, so the operating system's ruling with an iron fist. Okay, we are kicked off the CPU. As we're packing up our bags, as we're context switching off the CPU, we can roll back our program counter 1. Now, to do that, we also have to consider the values of our registers that might change. So we really do need to kind of take 2 steps back in our little example in order to make sure everything is in the correct state. But we could roll back the instructions so that the next time through, we pick up where we left off and have to recheck that lock. instead of checking the lock, getting kicked off, coming back in when we already think the lock is open. So that's one way of combating it. Another way is we can give them a little bit extra time. Is one better or worse than the other? What do you think? Which of those seems more reasonable in our little example? Because one of the fun things with operating system design is you can sit around and you can come up with, one scenario, come up with a fix for that, and then come up with another scenario that breaks that fix. Hence blue screens of death. Or if you were a Mac OS 9 or earlier user, a operating system that literally did nothing, but the mouse still moved. That was always great when you came back to your computer and it was 10 in the morning, but the clock said 1:36 a.m. The mouse was still working perfectly. It's basically brain dead. Which is better, roll back or let it finish? What's the benefits of rolling back? Well, yeah, it's got to be a toss-up, right? If it's almost done, it would take less time just to let it finish. Let's say it was one cycle short. Okay, if it just got started, it's better to roll back. I mean, it's probably a coin flip at that point. What's the danger of letting it finish? So let's use our example here. Let's just say we let it finish. So I'm the process that's grabbing the resource. So I've checked it. I've opened the door. CPU or the operating system tries to kick me out, notices I'm mid-instruction, goes ahead and lets me finish. I step in, lock the door. And now I'm kicked off the CPU. What's the downside to that? Yeah, I have a resource, but I've not provided CPU time. Okay. So, I don't think we need to go into the example of the outhouse for this one, but you run in, lock the door, and you've chosen not to go. You're just standing there. Okay, so now in computing time, maybe this isn't a drastic amount of time. A human being might not necessarily notice. But if one of the goals of an operating system is to be as efficient as possible with our operating system, keep the CPU as busy as close to 100% of the time as possible, let all our resources be used as close to 100% of the time as possible, the fewer things that are idle, the better. That's the real goal of an operating system. We don't meet that goal hardly ever, okay? Unless you're mining. And you might meet the goal with the CPUs. But generally speaking, that's our goal that we always come up short on. But we would consider it to be, go ahead.
So if you go through, get the resource, and then you're kicked off, if that process ends, can't that damage the resource? Or will it automatically unlock the resource if it realizes that process ended?
Well, what do you mean by damage the resource?
So like say you're taking a file and you gain access to it, and then you're kicked off the CPU, and you still have access to the file, but you're not allocated CPU time. If that process ends, does that file stay locked?
It would. The last thing you did to it was lock it. So if the next guy who tries to go and gain access to it's going to find a locked door.
So can't that just keep that file or that resource or file in limbo?
It is. It's in limbo until the guy who just locked it gets it again. Because then he's the only guy who has marked that he has gained access to that resource, and he will just pick up where his critical area, which I've mentioned before, the stuff he's going to do with that resource before he relinquishes it. So we could say that's inefficient because we don't want to let somebody lock a resource and then leave the CPU, especially if they're waiting for some user interaction and the user walks away for lunch. So, I mean, there's a whole lot of what-if scenarios here, but those exist in operating systems. So now you have somebody who walked off for lunch, and it's going to be 2 hours before anybody can open that file because they left the file open. That makes sense? Now, that can actually exist on, you can have that exist on kind of low-security network drives. Somebody can open a file on their computer, leave it open in Microsoft Word or something like that, walk away, and depending on kind of the version and what kind of security is on the network file system, if somebody else hits that same drive, tries to open that same file, it might say this file cannot be opened because it's currently locked. Somebody else is using this resource. Okay, and they've left it open on their computer overnight. Okay, and they just left for a 3-week vacation. Okay, again, extreme examples, but not impossible examples. Okay, so we're starting to see that these are legitimate problems. It seems like such a small little problem that in real life, we're able to kind of just handle that as people, right? If 2 people get to the door of the bank at the same time and you both try to grab the handle, you say, oh, after you. Just politeness fixes it, right? But computing is far more specific, right? They're not nice. One process isn't nicer than another process. They're all trying to follow the exact same script on how do they do things. Makes it very interesting. Now, in the future, we might have, I think might is probably the wrong phrase. I think we'll very likely have artificial intelligence-based processes that will make decisions more human-like, but in the moment. So if 2 things try to grab access to the resource at the same time, they become aware of each other, and one of them chooses to back off. Now, that does already exist. We do have we have priorities in an operating system. So certain processes have higher priorities than other ones. You've maybe seen on Windows, you can run a certain application as administrator, something like that. So that runs it with a higher priority, whatever that ends up meaning for that operating system. But generally speaking, if there's a race condition involving a higher priority process and a lower priority process, the higher priority process will probably be given that resource. That will be part of the handshaking that's involved in alleviating the race condition, resolving the race condition. That make some sense? So we have all sorts of different approaches we have to look at in terms of how do I keep more than one thing from accessing a resource at once? Assuming you have a resource where that's a problem. Now, if we attach this to let's see, it's going to let me do another slide now. Man, that's just really annoying, isn't it? I clicked update on you. Why aren't you happy with that? Maybe the network's down. Who knows? Okay, well, so let's think about this from our chat server perspective. So we've decided we're going to approach this from a shared memory perspective. So our shared memory is probably going to be a collection of messages and the order in which those messages have shown up, right? Okay, so so we're going to have to give ourselves a big chunk of memory that's going to be representative of the most amount of messages that might be in this chat room. So we're already dealing with a kind of a poor logical approach to begin with. But for us, that's going to be okay. We're not all that chatty, right? So we'll leave, I think giving ourselves 50 messages back and forth will be plenty for our testing. We're not going to be that. So now we have this shared resource that can have up to 50 messages in it, right? But now you have 3 children. Let's say 3 people that are in the chat room. And even though each child is, if I'm one of the children, my user is typing in hello, pressing enter. We're going to add that. So if we think of that as a queue of messages, we're going to add that to the end of the line, the end of the queue. That's the next message that she gets spit out, right? But now all of these other processes are going to be having to check that same shared memory. Now, we certainly don't want anybody to read from that queue at the same time as we are writing to that queue, because we don't want process 2 to show all the messages but miss the message hello that we just put out there. But process 3 and 4 both got the hello message just because of luck of timing. Does that make sense? So how might we combat that by having this single resource? We kind of have a single bucket here in the middle that, or a single piece of paper, that's probably the better way of thinking it, with 50 lines on it. And that piece of paper has in it the, however many messages have been sent up to this point. How do we prevent, or how does process 1 know which is the next message they haven't seen? from that versus process 2, how do they know, versus process 3, how do they know? This would be similar to like the program counter for a PCB, right? They might just keep track of which line number was they last accessed. So reading from it actually isn't really a problem. So if we think about giving ourselves shared access to things, reading is rarely the issue. It's writing that's the issue. We do not want more than one process to write to that resource at the same time. We don't want process 1 to say hello, process 2 to say goodbye, and both of them write that to bucket 5 of our shared memory. Because whoever wrote it last is going to be the one who gets that's the permanent one, right? They'll overwrite the previous one. So it's writing to that resource, modifying that resource that we need to protect against. Now, based on what we know right now, just with the tools that we have available to us right now, so we're rolling back in time to the early days of multi-process programming. Even though I've thrown out some buzzwords, we've talked about semaphores at the very high level, and we've talked about locks and other things like that. We don't know how to do any of those things yet. So just the tools that we currently have in our toolbox, how can we protect that shared memory from having more than one process write to it at the same time? What are some tricks you might try? And we'll even throw this out there. We're trying to prevent race conditions, not necessarily guarantee we won't have a race condition. We're limiting the possibility, reducing the possibility of a race condition. We need to, go ahead. Okay, but how? How do we protect that? If I have this notebook here, okay, and the 4 of us are all trying to change something on that notebook at the same time, how do we guard against who gets access to the notebook? What are some things we can do that would allow us to decide who gets, and we have to kind of connect this back to computing, because with humans, we might say, oh, go ahead, you go first. And I'll just go after you, it's fine, and you get to be last. Like, look, I didn't make the rules. So, we might do something like that. But generally speaking, if all 4 of us want to write to that, how do we gain access to that resource? And then keep the other, how does one of us get access to that resource, but keep the other 3 from having access to that resource, using only the little magic tricks that we currently have in our tool belt, if we're trying to kind of almost create a little hack solution to protecting this resource? Okay, so kind of maybe just have a variable that's either a 0 or a 1, something like that. We kind of feel like changing of contents of a variable from a 0 to a 1 might be fast, closer to atomic, something like that. So instead of only the person who has who reads from that variable and gets a 1 gets access to that. Everybody else has to wait till it counts back down to a 0, something like that. Make sense? So whoever grabs it at a 0, they flip it to a 1, which we hope is close to atomic. And then they can go use that resource. All these other ones, they're still seeing a 1 there. So they can't access it. They're checking. Finally, this guy's done writing. He flips his 1 back to a 0. Whichever one of those other 3 grabs it next, then gets that resource, flips it to a 1. All right? So we're going to write our version of that next time. And I think we're going to find that we won't have race conditions with that. But we're also going to discuss that race conditions are possible. And then we'll replace that variable with a semaphore. Where at the end of the day, a semaphore is actually an integer, like we just discussed, that's guaranteed to act atomically. To pretend like it's atomic. All right? Remember, no class on Monday unless you have a class after 4 p.m. So the next time I will see all of you will be next Wednesday, right? If you're traveling, travel safe. I will see you next Wednesday.